Hi. In the second segment that just concluded, I described to you the initial stages of an innate immune response where a cell begins producing interferon, and that signals to the neighboring cells that, hey, there may be a virus lurking around this neighborhood. Lock your doors and batten down the hatches because you don't want that virus coming in here and copying itself. What I'm going to do now is describe the second part of the innate immune response, a more very generalized response. So imagine that this cell here that we've been discussing, it becomes infected, it produces virus, it's producing interferon to fight the virus, but eventually, in many instances, that cell will just die. And when it dies, all of its contents, essentially the cell bursts, and all of its contents leak outside. So this would be RNAs, proteins, all the different components of the cell end up outside floating around. Now there's innate immune cells that are in tissues that are constantly surveilling the environment. And we'll talk about some of them, I believe, in the subsequent lecture, but we have dendritic cells, which I'll talk about. There's macrophages, there's mast cells. And these cells, particularly macrophages, are constantly going around vacuuming stuff up. And they're looking for signs of an infection. Now, when you have cells bursting and releasing their guts, if you will, that's a sign usually that there's some form of stress in that tissue. And stress is often a byproduct of having a microbial infection. So that's a warning sign right away to these cells of the innate immune system in the tissue that, hey, there's probably something going on here. And so then they react by producing a series of proteins that are known as cytokines. And these are like hormones for the immune system. Cytokines get secreted from the innate immune cells that detect this stress, and they can act on cells of the innate immune system, the adaptive immune system, and even cells that are part of normal tissue. And one example of how they work is drawn below here. So this just shows blood vessels that may be feeding this tissue with blood, with nutrients, with oxygen. And here's a normal blood vessel in a normal tissue. And what you can see is that the normal blood vessel has a narrow diameter, and the blood vessel itself is made out of cells that wrap around to form a tube, like, say, the cardboard roll that you have for paper towels. And these cells have very tight junctions between them. They seal up close together. And what that does is it prevents the contents of the blood from leaking out of the tube, all right, which makes perfect sense. However, once you have activation of this innate immune response and all these cytokines floating around, some of those cytokines in particular act on blood vessels to do two things. Number one, they cause the blood vessel to dilate, so the blood vessel just gets wider. And, in a very simplistic way, a wider pipe can carry more water. So the wider that blood vessel is, the more blood can flow through the tissue. And that can help bring more cells and proteins to assist in a potential fight against a foreign invader. Now, the other thing that those cytokines can do is weaken the contacts, loosen the contacts between these cells, such that components that are in the blood, like cells and proteins that I've been referring to, can now leach out of the blood. Here I've just shown a few proteins, some cells leaching out, and these proteins could potentially include molecules that would assist in the battle against this incipient viral infection, as well as other innate immune cells and cells of the adaptive immune system, which can also join the fray and help combat that virus. And so these two things, the widening of blood vessels to give you increased blood flow and the loosening of the contacts so that fluid can seep out of the blood vessel, lead to two of the very common manifestations of inflammation. The first being that the tissue gets red, and it gets red because there's simply more blood flowing there. and it swells, and it swells because the blood vessels get leaky and fluid is leaking out into the tissue. Now, that's a good thing for the reasons I've stated. You're bringing more weapons to the fight, if you will, but this response can get over-exuberant, and you can imagine in the lung, if there's a lot of fluid coming out, that could eventually cause problems in the lung with breathing, just that fluid accumulation. So we'll discuss in the last lecture that there are some strategies to sort of tamp that down, and those may be beneficial in certain circumstances when people have an infection. Now, the innate immune system is a key component of our arsenal to fight viruses, and we know that because in mice, if you disable it, those mice are now susceptible to, a variety of different types of infectious agents, more so than a mouse that has an intact innate immune system. And in fact, for certain microbes and certain conditions, the innate immune system by itself, it can be sufficient to do the job. However, in general, the adaptive immune system also has an important role to play, and we could see that, just by looking at AIDS patients. An untreated AIDS patient essentially loses function in its adaptive immune system, and that person then is much less able to fight off infections. They still have an innate immune system and they can fight off some infections, but if they're not treated, eventually they will succumb to an infection due to the lack of having an adaptive immune system. So it's really this intimate collaboration between the innate immune system and the adaptive immune system that confers maximum protection to enable us to fight back microbial invaders that are everywhere in our environment. With that, I'll close out this segment, and I'll return shortly with the fourth segment of my fourth lecture on coronavirus. Thanks for your attention. Have a great day.